Spatial distribution of electrons in a cylindrical electric field. A wire of radius r sub 0 is coincident with the axis of a metal cylinder of radius capital R and length capital R. The wire is maintained at a positive potential of V stat volts. So we're going to do this in volts. With respect to the cylinder, the whole system is at some high absolute temperature T. As a result, electrons emitted from the hot metals form a dilute gas filling the cylindrical container and in equilibrium with it. The density of these electrons is so low that their mutual external electrostatic interaction can be neglected. Part A. Use Gauss theorem to obtain an expression for the electrostatic field which exists at points at a radial distance r from the wire, where r is between r0 and capital R. The cylinder of length L may be assumed to be very long so that end effects are negligible. So here is our cylinder, radius capital R, length L. Here is the wire inside that has radius R0, and the outside is grounded. Inside I have potential plus V, and I take a Gaussian surface here, that's this cylinder, and this is the top view. You can see that the electric field is pointing from radially outward from the center to the outer shell of the outer surface of the cylinder, and my Gaussian surface will look like this from the top. So I'm going to use Gauss Law. So what is Gauss Law? The closed surface integral E dot dA is equal to the charge enclosed, which I will call Q, divided by epsilon 0, because there is nothing in between the wire and the outer surface of the cylinder. I can use epsilon 0. So what is given that the radius of this Gaussian surface is r, what is E dot dA? It's going to be equal to E, electric field is in r hat direction, E in r hat direction, dotted with the area vector, which is 2 pi r multiplied with the length in r hat direction. So this will give me electric field E times 2 pi r L, that is equal to Q divided by epsilon 0. So I find that the electric field can be found in terms of the total charge that is in the wire inside. So it is Q divided by 2 pi epsilon 0 r times L. Now, however, I have the potential between the inner wire and the outer cylinder. So if I look at the potential difference between the potential at r equals capital R minus the potential at r equals to 0, if you wish, because it doesn't matter if it's r equals 0. The inside cylinder is an equipotential surface, so I can take it at the center. So this is minus the integral from 0 to capital R E dot dl. So I go from 0 to capital R E dot dl. So the potential at r equals capital R is 0. Potential at r equals 0 is V. And here I have minus the integral from 0 to capital R. So let me take the constants outside. Minus Q over 2 pi epsilon 0 L integral from 0 to R dr over R. So my dl vector is dr in the r hat direction. So dl vector is dr in r hat direction. So if I perform this integral, so basically I find that minus v, so the minus signs cancel, so this is going to become plus v. V is equal to Q divided by 2 pi epsilon 0 L natural logarithm of R divided by 0. So that's what I would obtain here. So instead of doing it from 0 to R, let's do it from R0 to R. So the potential at R0, R equals to R0 is what I'm taking as the reference, because otherwise I cannot do it. The potential difference between R equals R and R equals R0. So this will be natural logarithm capital R divided by R0. That will be the result of the integral. So I will find that what I'm calling Q, the charge enclosed, is going to be equal to 2 pi epsilon 0 L V divided by natural logarithm capital R over R0. So since the electric field was given as a function of R as Q divided by 2 pi epsilon 0 LR, I substitute for Q this result. I find that 2 pi epsilon 0 LV divided by natural logarithm capital R over R0 multiplied by 1 over 2 pi epsilon 0 LR. So that's going to be the electric field as a function of R. So here you can see 2 pi epsilon 0 L, 2 pi epsilon 0 L will cancel, and I will find that the electric field, the electrostatic field, as a function of R, let me write this in vector form, can be written as the potential V, potential difference V, divided by R natural logarithm capital R divided by R0. And this is, I want to write this in vector form, this is in R hat direction. So the electric field is V divided by R natural logarithm capital R over R0 in R hat direction. So this is for R between R0 and capital R. So that's also why I had to do this integral between R0 and capital R here, because I'm not talking about electric field inside the wire. Okay, so therefore the correct thing to do is to take this integral from R0 to capital R and calculate the potential difference between R0 and capital R. So this is the answer to part A. The electric field is given by this expression. Now in part B, in thermal equilibrium, the electrons form a gas of variable density which fills the entire space between the wire and the cylinder. So the electrons are boiling off from the metal inside, and they're filling the space between the cylinder and the wire. So using the results of part A, find how the number of electrons per unit volume depends on the radial distance r. Okay, so what I need to know is how the potential changes as a function of r. Now the potential at r minus the potential at r0, or minus the potential at capital R, let's say, will be the integral from, so because I want to go in the radially outward direction, let's do it from capital R to, let's find the potential difference between capital R and R. This is minus the integral from R to capital R, E dot dr. Because electric field is minus the gradient of the potential, so that's what I'm using here. the potential at R is 0. Potential at R equals lowercase r is what I'm trying to find. This is the integral from, let me put the constants outside, v divided by natural logarithm capital R over R0, integral from R to capital R, 1 over R, so it's going to be dr over R, because electric field is in r hat direction, dr is in r hat direction, so that's going to be dr over R. Once again, my minus signs will cancel here, and I will find that the potential as a function of R is given as v times natural logarithm capital R divided by R divided by natural logarithm capital R divided by R0. So this is what I will find for the potential as a function of R. So you can see that when R is equal to capital R, the potential is 0. When R is equal to R0, the potential is V. So let me check. When R is equal to R0, I will have a natural logarithm of R over R0 divided by R over R0, so it will give me 1, so phi is going to be equal to V. When R is equal to capital R, on the other hand, I will have natural logarithm of 1 at the top, so the potential is going to be 0, so this checks. So this is the radial dependence of the potential. So when I have an electron inside this potential, so these electrons have boiled off and filling the space in between here, so I have these electrons and they are subject to this potential, so I can find their energies. So an electron has a potential energy at position R, radial position R, which is given by the energy is equal to the electron charge E. So let me put minus E here, minus E times phi as a function of R. So that's the potential energy. So this will be equal to minus EV natural logarithm capital R over R divided by natural logarithm capital R over R0. And E is what I'm calling the electron charge, is 1.6 10 to minus 19 coulombs. So I've already taken care of the minus sign here. Now the density of electrons at position R will be proportional to the probability of having the electrons at this position, because when we find the number of electrons that have a certain energy, we multiply the probability with the total number. So basically the density is proportional to the probability. So we can write the following: the density of electrons will be a constant times e to the minus beta epsilon as a function of R. So I find that therefore, if I substitute the energy here, this is going to be C times exponential. Now I have a minus beta here, and there's a minus sign, so it's going to be plus beta, beta EV, natural logarithm, capital R over R divided by natural logarithm, capital R over R0. So it should be in this form. Now I can see that inside the exponential I have a natural logarithm, so I want to play with this expression a little bit. So if I rewrite this, n of R is a constant C times exponential, let me separate the two terms here, beta EV divided by natural logarithm capital R over R0 multiplied by natural logarithm r, capital R over R. So I'm going to call this this part, the first part A, the second part B. So I realize that this is C times exponential A natural logarithm B. So mathematically this is equal to C times exponential natural logarithm B to the power A. So if I continue here, I can see that n of r can be written as exponential natural logarithm b to the power a is just b to the power a. So it is c times b to the power a. So it is c times, what did I call b? I called b, so let me be careful here. What I call b here is capital R over R. So maybe it's better I write this explicitly here. B is capital R over R, and what I'm calling A is minus beta EV divided by natural logarithm capital R over R0. So with that, I have capital R over R, B to the A, no, A was plus beta EV divided by natural logarithm of R over R0. So it's capital R over R to the power A, which is beta EV divided by natural logarithm capital R over R0. So let me rewrite it here to make sure I have the right answer. It's a constant times, or we can say it goes as capital R over R beta EV divided by natural logarithm capital R over R0. Or you may find that this can be written as because natural logarithm of R over R0 is minus natural logarithm of R0 over R. We can also rewrite this as, if I have this in natural logarithm R0 over R, I will introduce a minus sign, so that will flip the capital R and R. So I can write this also as R divided by capital R beta EV natural logarithm R0 divided by capital R. So this is just to have R in the numerator, I have rearranged it. This is basically the dependence of n, the electron density, as a function of radial distance. So let's take a look at part C. Give an approximate criterion determining how low the temperature must be so that the electron density is small enough to justify the approximation of neglecting mutual electrostatic interaction. Now, to answer this question, I want to know what is the interaction energy. Well, the interaction energy between two electrons is the interaction energy between two electrons separated by a distance r is the potential energy, Coulomb's constant, Ke square divided by r. So there is the potential created by one electron at distance r. The other electron sees this potential and has this potential energy, Ke square over r. The force is Ke square over r square, but the potential energy is Ke square over r. And how about the energy of the electrons? The energy of the electrons in the electron gas are roughly the thermal energy, because it's maintained at a high temperature T. The thermal energy is kT. So if I have this interaction energy Ke square over r, much less than the thermal energy, the interactions, the mutual interactions can be neglected. So this would be the criterion for neglecting the mutual interactions between electrons. So what is the average distance? So let me make this the average distance between electrons. So r pi, and let's call this average distance r. So if I have n electrons per volume, how can I estimate the average distance between the electrons? So this is r, the average distance between the two electrons will be approximately n to the power minus 1 over 3. Why is that? Because remember, we were thinking about when we try to calculate the average distance between atoms, for example, we thought about forming a cubic crystal out of these atoms, and this was our model, and we said if this is the average distance between the atoms, we have 1 over 8 times 8 atoms. So for in this case we have electrons per cube, and we can basically say that there is 1 electron per cube. The volume of the cube is total volume is average distance r cube. So if I have 1 electron per cube, so if I have capital N electrons will occupy capital N times r cube volume, which is the total volume, or let me call it Vtotal. So you can see that capital N divided by Vtotal will be equal to r cube, or the average distance is n to the power minus 1/3. So that's how we estimated the average distance between atoms in a crystal. So we're using the same type of approximation for electrons in order to estimate the average distance between the electrons. This is the simple cubic model. Then I have ke square divided by n to the power minus 1/3, ke square over r, should be much less than kt, or I can say that forget about the k, so we can have n to the 1/3 e square should be much less than kt. So this could be the criterion to neglect interactions between electrons. So this is basically telling us how low the temperature can be. Okay, so going back, we have a wire with radius r0 that is inside a cylinder, metal cylinder with radius capital R. The space in between is empty. The wire inside is kept at a potential plus V with respect to the outer surface, which is grounded. And first task was to calculate the electric field between these two surfaces. The Gauss Law tells me that closed surface integral eta dA is q over epsilon 0. The electric field lines will be pointing radially outward. There will be no contribution from the top and bottom surfaces, only contribution from the side surface, which is going to give me total charge enclosed q divided by epsilon 0, because there's nothing in between. So electric field is in r hat direction. The dA vector is 2 pi r. The integral of dA vector gives me 2 pi rl in r hat direction. The electric field is constant at position r, so that's its It only has a radial dependence, so it comes out of the integral. So this gives us E times 2 pi RL is equal to Q over epsilon 0. And the potential difference between R equals capital R and R equals R0 is minus the integral R0 to capital R E dot dl. So I find that the potential difference is Q over 2 pi epsilon 0 L natural logarithm capital R over R0. Now I can find the electric field. I can eliminate the Q from the electric field expression and find that it is V divided by R natural logarithm capital R over R0 in R hat direction. So you can see that R is less than capital R and greater than R0. This is going to be a positive value for the electric field that is pointing radially outward. And in part B, I was supposed to calculate how the gas electron density changes with radial distance. For that, I calculated the potential difference between the outer surface and the radial distance r from the center. That is minus the integral from r to capital R E dot dr. Electric field is minus gradient of the potential. And I found that the potential as a function of r is V times natural logarithm capital R over R divided by natural logarithm capital R over R0. I also checked the limits R equals R0 and R equals R, and this seems to work. So an electron has a potential at position R, which is has a potential energy at position R. So let me correct this. So it sees this potential multiplied by E gives me the potential energy it's going to feel, which is minus EV natural log capital R over R divided by natural log capital R over R0. And the number density of electrons at position R will be proportional to the canonical distribution, the probability of having the energy at position R. So basically it tells me the distribution of electrons over different energies is reflected in the distribution, radial distribution of electrons. So I substitute for the energy of the electron the potential energy, and by doing some math here I find that the radial dependence of the electron density is R over capital R to some power. Now, when can we neglect the interaction between two electrons? The interaction energy between these two electrons is the potential energy Ke square over R. This K is not the Boltzmann constant, this is Coulomb constant, right? So it's it's 1 over 4 pi epsilon 0. It's basically the Coulomb constant. And if the energy of the electrons is high enough, so the thermal energy is high enough, I can neglect the potential energy. So Ke square over the average distance between two electrons should be much less than Kt. And for the average distance between two electrons, to estimate that, I use my simple cubic model, where I estimate the average distance between two electrons as the electron density to the power minus 1 over 3. And this gives me this criterion gives me n to the power 1 over 3 E square should be much less than Kt for us to be able to neglect the mutual interaction between electrons.